Welcome to this explainer, where we're going to completely demystify hydrocarbons. We'll be moving from their massive, everyday macroscopic uses all the way down to the tiny 3D molecular bonds that hold them together. I am super excited to take you on this journey, zooming in from the huge scale of the world around us right down to the microscopic architecture that literally builds our modern world. Okay, let's just dive right into this by asking a pretty simple question. What connects everyday things like LPG, CNG, the petrol in your car, and even the polymer plastics in the phone you're probably holding right now? Take a second to really think about it. We interact with this stuff constantly, but we rarely pause to consider the invisible chemical foundations that make them all function. Well, the answer is hydrocarbons. These are the fundamental chemical structures powering our homes, running our vehicles, and, honestly, building our modern world. From the compressed natural gas in city buses to the solvents in your paint and the polymers in your electronics, hydrocarbons are the literal building blocks of our daily lives. Today, we're taking a mini masterclass on organic chemistry to see how they work. We'll meet the hydrocarbon family, explore the stable alkanes, learn how to name and shape them, see how they react, and finally, introduce double-bonded alkanes and their isomers. Let's jump right in. Starting off with Section 1, meet the hydrocarbon family, looking at the carbon and hydrogen basics. As the name brilliantly illustrates, these are compounds made of only carbon and hydrogen. That's literally it, just two elements. But the crazy thing is, they combine in incredibly diverse ways. Depending on the types of carbon-carbon bonds they form, we classify them into saturated, unsaturated, and aromatic categories. It's an entire universe of materials built from just two atomic puzzle pieces. Let's zoom in on our first character in Section 2, alkanes, the stable, saturated paraffins. I actually like to think of alkanes as the stubbornly stable, almost boring older sibling of the chemical world. They're saturated, which means they only contain carbon-carbon single bonds, following the general formula CnH2n+2. Because of these single bonds, they're highly unreactive under normal conditions. In fact, historically, they were called paraffins, which comes from Latin meaning little affinity. They really just don't like to react with acids or bases. Structurally, they form this highly predictable tetrahedral 3D shape. Take methane, for example, with its perfect 109.5-degree angles. Moving on to Section 3, naming and shaping alkanes, where we translate the chemical code. Now, we don't need to get overwhelmed by complex chemical names here. You just follow a highly logical 4-step IUPAC process. First, find the longest continuous carbon chain. Second, number the atoms so your substituents get the lowest numbers possible. Third, attach your alkyl groups. And finally, just fill in the remaining bonds with hydrogen. It's really just a satisfying structural puzzle. When it comes to how they act in the real world, alkanes are completely nonpolar molecules. This is due to the covalent nature of their bonds and the minimal electronegativity difference between the carbon and hydrogen atoms. This nonpolar nature gives us that famous chemical rule, like dissolves like. This explains perfectly why you need a nonpolar solvent, like petrol, to clean a nonpolar grease stain off your clothes. Water just absolutely won't work. But what's truly fascinating is how their physical shape impacts things like boiling points. Look at this. The boiling point drops drastically, even when the molecular mass is exactly the same. Notice how a continuous pentane chain boils at 309.1 Kelvin. But as we introduce branching with 2-methylbutane and then the highly branched 2,2-dimethylpropane, the boiling point steadily falls all the way down to 282.5 Kelvin. So what's going on here? The crucial takeaway is that as branching increases, the physical shape of the molecule literally changes. A continuous chain has a large surface area, which allows for stronger intermolecular van der Waals forces. But as you add branches, the molecule morphs into a much more compact, spherical shape. Spheres naturally have smaller contact areas, which shrinks those van der Waals forces holding the molecules together. Weaker forces mean less heat is required to break them apart. Makes sense, right? Okay, before we move forward, let's test your spatial thinking a bit. Imagine holding a single ethane molecule in your hands. If you grip the two carbon atoms and twist them around that single carbon-carbon axis, what do you think happens to the hydrogen atoms attached to them? Well, because they exist in 3D space, twisting them creates infinite spatial arrangements called conformations, or conformers. You can rotate them freely between an eclipsed state where the hydrogen atoms on the two carbons are perfectly aligned and as close together as possible, and a staggered state where they're rotated to be as far apart as possible. The molecule is just constantly spinning, fluidly moving through these infinite spatial arrangements at room temperature. That brings us to Section 4, how alkanes react.
and how we force those stubborn bonds.
Even the most stubborn alkanes can be forced to react under the right conditions. Halogenation brilliantly illustrates how to break these stable molecules using a three-step chain reaction powered by ultraviolet light or extreme heat. First up is initiation, where that energy breaks a chlorine molecule into highly reactive free radicals. Next is propagation. These super aggressive radicals attack a stable alkane, like methane, stealing a hydrogen and creating a methyl free radical. That radical then attacks more chlorine, setting up a continuous loop. Finally, we get termination. This happens when the free radicals happen to collide and consume each other, completely stopping the chain reaction.
Now let's switch gears for section 5. Alkenes, the double bond, a reactive sibling. Let's compare the two directly. If alkanes are the boring older sibling, alkenes are the edgy, highly reactive younger sibling of the hydrocarbon family. Unlike our stable alkanes with their single bonds, alkenes are unsaturated, featuring at least one carbon-carbon double bond, following the formula CnH2n. That single change shifts everything, leaving them relatively unstable and constantly hungry for electrons. The real secret to their reactivity lies in the physics of that double bond. It actually pulls the carbon atoms closer together, down to 134 picometers compared to 154 in alkanes. But here is the absolutely critical part. This double bond is actually made of two different types of bonds. One is a strong sigma bond. Think of it like a really firm handshake via head-on overlapping. The other is a weak pi bond formed by sideways overlapping, which is honestly more like a loose high five. That weak exposed pi bond acts as a source of loosely held mobile electrons. It essentially paints a giant target on the molecule for other chemical reagents, known as electrophiles, to attack. Finally, section 6, alkene shapes and isomers, exploring how they are locked in space. Remember how single bonds in alkanes spin freely, kind of like a wheel on an axle? Well, the double bond changes all of that. It locks the carbon atoms rigidly in place. You literally can't twist a double bond. This creates distinct, strict physical geometries depending on which side the attached atoms or groups sit. We call this geometrical isomerism, leading to fixed cis and trans configurations that have completely different physical properties from one another. What's really cool is that chemists can actually exploit these rigid shapes. For example, using a highly specific recipe called Lindlar's catalyst, which utilizes deactivated palletized charcoal, they can take an alkyne with a triple bond and partially reduce it by adding calculated dihydrogen. The incredible result? They predictably and reliably build alkenes with exactly a cis geometry. It's literally architectural engineering at a microscopic scale. So, as you go about the rest of your day, I challenge you to look at the world around you and wonder what invisible 3D molecular bonds are quietly powering your life. Are you sitting near nonpolar alkanes? Or perhaps interacting with the rigidly locked geometry of alkene polymers? The microscopic architecture is everywhere, holding our modern world together. Thanks so much for joining me on this explainer, and keep exploring the fascinating structures all around you.